my talk will be about resource allocation in the cloud. But before I do that, I would like to thank the organizers for inviting me. I really enjoyed yesterday in Paris. I first went to a place where I usually go, to a Musée d'Orangerie, but I was really badly disappointed because the Musée d'Orangerie was the only place on earth where a professor, a university professor, did not have to pay in order to get in, and they canceled it. And I don't know how you guys approved this, but you know, we have very little respect around the world, so this was the only place, and maybe you can send a letter or something. After that, I went to the Pantheon, and I paid my respect to Lagrange, whose theory I use very frequently recently in my recent papers. So it was really great, and I thank you very much for inviting me. Anyway, we have to talk about some stuff that is related to the cloud. So this is data from 2012. We did not go further into 2013 and 14, but I think you'll see the same phenomena in I think the last one was March 2014. All the major cloud providers adjust the prices at the same time. Okay? In a matter of 2 weeks, all the major cloud providers just reduce the prices. So in 2012, it happened in March and in December. And I think in 2014, I remember it happened, the most recent cloud price reduction that was synchronized across all providers was in March 2014. So it's a multi-billion market, and everybody are racing on the pocket of the clients. And so what I want to do in this talk, I want to try to ask, where is this all going? If we are not talking about infrastructure as a service, which is modus operandi, you get bare machines, you get bare hardware, and you put your stuff on it. Where does it go? What's the next thing that it's converging to? And we identify basically 4 trends. And I'm going to talk about each of these, and I'm going to suggest that the solution for all these trends is in what we call resource as a service cloud, which is a concept that we published a few papers recently about, and this is where I'm aiming. All right, so let's talk about trend number 1. Trend number 1 in the cloud, in infrastructure as a service, is shrinking duration of rent. So we started by purchasing hardware, and when we purchase hardware, it remains ours for years until we throw it away to the garbage cans. Then for web hosting, the duration was reduced to month. The renting duration was reduced to month. And then when Amazon first proposed EC2 as a pay-as-you-go infrastructure, they talked about hours. So we were charged by the hour when we use the resources. But very soon later on, in 2009, the duration was already shrunk to minutes, to 5 minutes. And 3 years later, the duration was already shrunk to 3 minutes. And in the same year, ProfitBricks and Google App and the computer engines already started charging by the minute, by a single minute. And the analogy that we have here is the car rental companies, where we have companies such as Car2Go that are now charging by the hour, not by the day. And the telecom companies were court orders and the public pressure. They drove the telecom company to reduce the charging granularity from minutes to seconds. So what is going on here? What's happening is that the clients want to pay only for what they are using. They do not mind that you have a problem to charge them by the minute or by the second or by the hour, and you have problems in billing and collecting the data. They want to be charged only for when they use the infrastructure. All right, so our speculation is that this tendency, this trend, is going to continue, and that the duration of rent is going to be reduced for lower and lower until it reaches seconds. Okay, and we extrapolate that cloud resources will be rented by the second very soon. Okay, trend number 2, flexible resource granularity. So most cloud providers nowadays, they sell fixed bundles. They call them instance types in Amazon or server sizes in Google and so on. And sometimes they allow, in a very restricted way, adding and removing resources on the fly, but not while the application is running. You have to stop the application, you buy a larger bundle, and then they start your application again. Nothing is really happening dynamically, all right? But we see a tendency for, again, the clients make it effectively using a lot of pressure on the providers to provide flexible bundles. Because if you rent a fixed bundle, then either your requirements are lower than the fixed bundle that you rented. You rented it yesterday, and now you either need less than what you already rented, so you pay too much, or you need more, in which case you're stuck. All right, so the trend that we see is towards more and more dynamic and flexible resource assignment in a way that eventually will lead to applications being able to rent and discharge resources on the fly as they are running. Okay, so this is very important because clients want to pay only for what they use. And cloud providers, as I showed you on the first slide, they fight on the clients, and they fight now because they know that client commitment is going to be very strong. Once you have all your petabytes on a cloud, it will be somewhat hard to move them. So they fight now, and they fight hard, and if clients want to pay only for the resources that they use, and they want to rent the resources dynamically and discharge it dynamically, then cloud providers are going to allow it eventually. Okay, so this is the second trend. Third trend is a little bit more subtle, which we call service level agreements. So most cloud providers nowadays supply only either the resource is available or it's not available. But there are other levels of availability that we can talk about. And we call it quality of service, but it's actually the amount of availability of the resource. And the availability can be, I mean, nowadays when you rent a resource from the cloud provider, it's available for you 100% of the time. And I'm neglecting the 0.0000001% when the cloud is not available. So nowadays, either the service is available or it's not available. And but it may not be the case in the future. In the future, you may want to rent as a resource and come up with a quality of service agreement that will state that the resource will be available 80% of the time. And 80% of the time is good enough for some of the clients, were not as rich and cannot pay for 100% of the time. Does it mean that the cloud providers will be able to use the fact that some clients want 80% of the time availability, some of them want 50% of the time availability, and some of them want 100% of the time availability? We think so. We think that the answer is yes. And this is incorporated in the model of the resource as a service that I will show later. So our extrapolation is precisely that. Client pressure for efficiency will drive providers to supply levels of quality of service, which is just the level of availability for 90% of the time, for 80% of the time. And the low quality of service clients will be willing to pay less than high quality of service clients. Okay? Once again, if I want the resource only for 80% of the time, I don't want to pay for 100% of the time. And this is something that will be made possible by quality of service agreements. All right, so we are going to have tiers. Richer clients and poorer clients, and poorer clients will buy resources in lower quality of service, and richer clients will buy services and resources in higher quality of service, and the whole thing will be layered in the market. Okay, last trend. We are talking about economic forces that are acting on the provider. And what are these economic forces? So I told you that the providers nowadays, they fight on the clients. Okay, they fight on client commitment. And in order to do that, they need to provide elasticity, and still they want to provide elasticity for the client, so they want to somehow take the rich clients that are able to pay more and give them more quality of service, allow them to expand and get more resources on the fly. Remember the first trends that I told you about, the first three trends. And by doing that, they actually take those resources from the other clients. And at different times, they give the resources to the other clients and take the resources from the first client. Who are the clients that were small to the provider? Who are the clients that will get resources exactly when they need them? These are the rich clients. What about the poor clients? The poor clients have lower quality of service. So it is possible to get the resources from them when the rich clients need them. So what the providers are going to do, they're going to put rich clients with high quality of service together in the same machine with poor clients with low quality of service. And in times of need, in times of high pressure and high demand, they're going to take resources from the poor clients and give them to the rich clients. We call it Robin Hood in reverse, because you take from the poor and you give to the rich. What does the provider is trying to do here? He's trying to pack together as many clients as possible into as little as possible machines. Because if you can pack twice the number of clients, twice the number of applications into the same number of machines, then your margins are up by 50%, by 100% actually. Okay, so overcommitment is the name of the game. The provider is overcommitting the resources to the clients. And the analogy that we have here are the air carriers. They oversell the seats for the planes. Why? Because they know that some of the travelers will not make it to the flight. And if they do make it, it pays for the air carriers to pay those clients, those poor clients who want to make some bucks, to pay them to stay at the hotel and fly tomorrow. Okay, the same thing will happen in the flight. We extrapolate this, the same thing will happen in the cloud. The cloud providers, in order to retain the margin, the profit margin, are going to pack as many applications as possible into the same machines and drive the utilization higher and higher and higher, so that they can use less and less machines which will make the margins larger and will enable them to reduce the reduce the price. So what do we have here, actually? I'm summing up all the trends. We have clients who needs to purchase resources on the fly dynamically in granularity of seconds. Okay, suppose they need, suppose the load goes up in a matter of 2 seconds. They need to get the resources immediately. All right, and there are many different and sophisticated considerations that they need to take into account in order to understand which resources they would like to rent. And there's a provider who are interacting together with, interacting with all of these clients. And he's taking resources from one client, giving them to another client. And also, again, we have lots of sophisticated economic considerations that need to be taken into account. So we think that both the clients, the applications, and the providers are going to use sophisticated decision-making procedures as core functions of what they do. So all of them will have economic agents that will take economic considerations into account. Some of them we heard in this workshop previously. So this is how we see the architecture of the resource as a service. This is a provider. It's a host. It's managing many guests in a virtualized environment. I don't want to get you into all the computer science terms, but a guest for me is an application, okay? And a host is the manager of the cloud. And what does the guest do? What does the client do? What does the application do? It has a strategic agent which it consults all the time about whether to rent or to discharge resources. And for doing that, it monitors its performance all the time, the performance of the application that is running, together with the demand. Okay? And there's also some valuation for the performance that needs to be taken into account. The valuation may be linear and may not be linear. Many times it's non-linear. But there's some valuation to the performance. How many transactions, how many pages did I access, and so on and so forth. And all of these, the monitoring, the performance monitoring, the valuation get as an input into the strategy advisor. The strategy advisor takes all those sophisticated economic considerations into account, and it communicates them to the as a request for rental or the request for discharge of resources, and it communicates it in granularity of seconds, okay, to the host. And now the host is also it also has its host agent and a decision maker that takes into account the value of this application, of this specific client, the availability of resources, the demand across the cloud, and so on and so forth. And the communicator just eventually implements the decisions that are taken by the decision maker, either supplying the resources or getting them back, and so on and so forth. Okay, so this is a general architecture. And once you agree that this is going to be the general architecture, the question is, can computer scientists actually implement such an architecture? So before I do that, once again, I want to tell you, forgot about these slides. The app agent, the application agent, what does it do? It changes the desired resources on a second-by-second basis. So it's acting all the time with all kinds of considerations, economic consideration. It negotiates resources with the other clients or with a cloud provider. It trades in the futures market. It sublets resources and so on and so forth. Just to give you one example for the complexity of the considerations that needed to be done, consider resources, consider this application who got some memory in the steal of a price, okay? So there can be several possibilities, but let me give you two. Suppose it gets a lot of memory, and this memory costed very little, and it's being assured that this memory is going to stay with the application for a long time. It can be that because it got a lot of memory, it can change algorithms for the application and use less CPU cycles. And now it can discharge some of the CPU and pay less for the CPU. Okay? On the other hand, it may be that the application is such that in order to use this extra memory, it needs more CPU. So now it goes to look for more CPUs to rent. And we call this complementing versus alternating resources and so on. I'm not going to get into that, just to convince you that the sophistication of the application economic agent is very, very high. The host agent, on the other hand, is even more sophisticated, is even more complicated. It takes optimization, it solves optimization problems on the fly, optimizations that are known to be highly complex in the computer science community, sometimes NP-hard and exponential optimization problems. All that is written here needs to be solved, needs to be optimized in a way that will what? The question is, what is the target? What is the goal? What is the optimization function of the host agent? The answer is the host agent wants to maximize the social welfare, or the social welfare is a formal term, but the happiness of all the clients. Okay, so the host agent is trying to give the rich all the resources they need. It tries to maintain, to keep the poor ones, because they may turn out rich eventually. It tries to keep everybody in the system, maintain the quality of service, and keep everybody happy. Okay, so that's the optimization goal of the host agent, and we formalize happiness in the term social welfare. All right, so summary of everything that I said. You need to divide the resources among selfish applications, which are black box. You don't know what are the considerations of the applications. The answer is give more to the guests, to the applications who need them more. Okay, this is the answer. But who knows which application need more the resources? How can the host compare between the benefits between different applications? How can the cloud provider maximize the happiness or the social welfare of the application without knowing which clients need the resources more? Okay, so what we do is we use auction theory to formalize everything. Auction means that if you propose more money, then it means then if I propose more money than Emmanuel, then it means that the resource is more important to me than it's important to Emmanuel. What is the problem here? There are many, many problems. There's lots of issues in taking the theory, which is huge, and implement it and solve all the problems all the way. There's partial information, the theory is limited, we don't know how to deal with repeated auctions, there are highly complex optimizations that are involved, There are additional dimensions that needed to be solved. There are attacks and collusions of several clients to get the money of another client. There are side channels and privacy issues and all kind of stuff that we deal with. I just want to finish by showing you how we started dealing with all that. We took the general architecture and implemented it only for memory. Okay, the implementation is called Ginseng, and it uses the same architecture, except that here below we have something that in a virtual system can move memory between clients and can do it efficiently. I want to summarize the positive results that I will not have time to tell you about. So we defined a new type of auction, which we call, let me see if I can, if I remember the shortage, MPSP, Memory Progressive Second Price Auctions. And we showed that it maximizes the social welfare for all applications, even for non-concave and non-monotonically rising applications, which is a very, very hard problem in game theory. And we also showed that, and I will not show you how we did all that, what we showed is that because we use progressive second price auctions, bidding the true valuation of for each client is the best way to go, the best course of action under some plausible assumptions, which are true, which are always true. If you talk about the evaluation, you try some non-concave evaluation function. For instance, you can try, this is a memory consumer application with valuation which is a square of the performance, which is very, very typical to situation when, of social interaction when everybody needs to interact with everybody else. And this is a dynamic memcached version of memcached, which is a well-known benchmark in our community. And you can see the step function, which is true for the highest side of the load. The lower side of the load has no step function at all. And with these two valuations, just wanted to show you what we can do. So here's the number of applications that we put on a single machine, on a single server. And here's the social welfare. And this is the blue and the bluish and the green are resource allocation, are the state-of-the-art resource allocation algorithms or schemes that people use nowadays. And we use our MPSP auction in Ginseng, and you can see that sometimes we can have a factor of up to 6 or 6.2 in supplying the best social, in supporting the best social welfare. And this is a true system. It's working. So Ginseng simulation is only by simulation, but Ginseng itself are machines that get requests for resources, in this case only memory, and they discharge the memory and get the memory and so on. And you can see that it's very close to the upper bound. You can always compute the upper bound. We compute the highest social welfare possible in the system. So you can see that we match quite well the upper bound. If you look at the other if you look at memcached with a quasi-linear valuation, then we can get up to 15.8 different factor difference in social welfare. What does it mean? This means that we can pack up to 12 applications in the servers that we use, while normal or nowadays resource allocation protocols can pack perhaps 8 applications, which means that we can do 50% more in squeezing the applications while maintaining the social welfare, while maintaining the happiness of the clients. Okay, and this is a true system, once again. So the conclusion is that the resource as a service cloud is the future cloud model. That's what we think. We think that all the trends converge to that point. We implemented Ginseng, we implemented it, we showed that we can match the highest social welfare in the system and can do overcommitment tens of percent and sometimes 100% more than known algorithms. But future work is enormous. Okay, so we now work on bandwidth allocation, and this is already a two-dimensional auction, and optimization there grows exponentially. We do also license allocation and CPU allocation. So we are working on an implementation, on actual implementation of a multi-resource Raas machine. We are already expanding this into migration, into horizontal scalability algorithms that will enable the cloud provider to play with the machines that are allocated to the clients. Play with them, like decide when to move clients from one machine to another, decide when to open another replica of the client on another machine, and so on. Better dynamic game theoretic mechanisms. The game theoretic mechanism, the auction theory that we now have, does not cover what we need, period. We're talking about repeated games, almost no theory available. And there's a lot of issues about security and privacy, because the application would not like the valuation function to be disclosed to other application, because once the valuation function is disclosed to different applications that share the same machine, then this can be used in order to, this can be used maliciously by a coalition of application to grab the money of the application whose valuation is known, using some tricks that I do not have time to talk here, and I think I talked too much already, so anyway.
Interesting talk, but my question is about memory, because you save everything on memory. Do you have any backups or any disaster recovery? Because if the system fails, you're going to lose all the data. Do you have some sort of machine learning or some sort of thing to recover the data, or some simulation or some sort of thing you have done before? Thank you.
So I don't know how to say that, but gently. But you need to know computer science when you come to visit new challenges. And with respect to failover and replicas and disaster recovery, we've been there. We've done that. We've been working on that for the last 30 years. It's solved. It's just working in a different layer of abstraction than what I was talking about now. So we are not trying to solve everything in the same abstraction layer. We leave this to mechanisms that were developed and are well known, and I myself published a few papers about that in like 15 years ago. Other people published a lot of papers about it. The solutions are well known. And you don't, if you try to mix everything together, I mean, there's already enough complexity here with new challenges of combining the economic optimization together with together with the systems considerations. If you put in also failover, forget it. And another remark is regarding the multiplicity of clouds. So if you are renting another cloud in order to make sure that your application gets another 9 of availability, this misses the whole point of why clouds are called clouds. The reason the clouds are called clouds because they should be completely black boxes that always support your requests and always support availability. All right, so if a cloud is unavailable, this means that many data centers in different locations already failed because the mechanism that the cloud itself tries to employ in order to preserve availability are already substantial enough for you to rely on the fact that the non-availability time is negligible. So I do not believe people are going to rent several clouds in parallel. This is not going to happen. The cloud provider needs to make sure that they never lose data. And if you think, if you're afraid that your data will be lost by cloud provider, you're not going to use this cloud provider. You're going to use a different cloud provider.